All right, today we're going to talk about the second fundamental theorem of calculus. Let's suppose that we define a function based on an integral. An example of this would be capital F of x will be the integral from 0 to x of e to the minus t squared dt, right? So this is the famous bell curve, and this function tells us the area between 0 and x there under the bell curve. That's what that function, capital F, would be. Capital F would give that area. And if we define capital F this way, what do we know about capital F? Does it have anything to do with that function inside there, right? Well, the answer is yes, we do know something about it, and that's what the second fundamental theorem says. So this is Theorem 6.2, sometimes called the second fundamental theorem of calculus. If little f is a continuous function on an interval, and a is any number in the interval, then defining a new function f of x by the integral from a to x of little f is a new function on the interval, and capital F prime is equal to little f. So the idea is this new function has a derivative, which is the original function. Okay. I'm not going to talk about why this is true. In the first instance, you might ask, why would you ever need to do that? Well, taking a look at an example, there's an important function from optics called psi of x, in which you need to integrate from 0 to x sine t over t dt. If you recall, there's a law about angles and whatnot with optics that involves expressions like this, so it's not too hard to believe that this could be important. There's no other way to write this function psi x except for is this integral from 0 to x of sine t over t. So that's just the only way to do that. This function I wrote at the beginning here, this capital F of x here, this is another function, sometimes called the error function, which there's no other way to write it, right? But what this does is this allows us to just use this new function and write things about it. So for example, we can take the derivative of x times psi x. By using the product rule, we know the derivative of x is 1. We would multiply that by psi x, plus x times the derivative of psi x. Well, the derivative of psi x is sine x over x by the second fundamental theorem. So this is going to be psi x, simplifying, plus sine of x. And so we can calculate that derivative. All right, so let's do a few more examples like this, right? If we define a new function by the integral from 0 to x of cosine t squared dt, and we want to take the derivative of it, derivative with respect to x, the fundamental theorem says, oh, this is just cosine of x squared. And we're good. Okay, now I'm going to show another one which is a slightly different situation. Let's take the derivative with respect to x from the integral 0 to x squared natural log 1 plus t squared dt. Okay, now this is where this gets a little bit difficult. The idea is if we define capital F of x as the integral from 0 to x, natural log 1 plus t squared dt, then we are taking d over dx of capital F of x squared. Okay? The fundamental theorem is only about integrals from one point to one variable x, not the variable x squared. So if we want to use the fundamental theorem, we have to only use it on this function f of x. We can't use it on f of x squared, but thankfully we have the chain rule. So this, recall, due to the chain rule, is going to be capital F prime at x squared times, by the chain rule, 2x. Capital F prime, by the fundamental theorem, second fundamental theorem, is natural log 1 plus x squared. So capital F prime at x squared is going to be natural log 1 plus x squared squared, which is x to the fourth, times 2x. So you see the difference between what happens. Just take a second and see the contrast between the previous problem and this problem, right? When you have just x in the integrand, you can easily use the fundamental theorem of calculus. When you have something more complicated in the integrand, then you have to use the chain rule. Okay, let's do an even more complicated version of this. Let's find the derivative with respect to x of the integral from minus x squared to x squared of e to the t squared dt. Okay, so this is kind of complicated because we have variables in both limits of integration. So we're going to deal with this very carefully. The first thing we're going to do is going to break it into an integral from 0 to x squared, and then negative x squared to 0. Why am I doing this? Because I cannot apply the fundamental theorem unless I have a constant as one of the variables of integration. Now I'm going to rewrite this, 0 to x squared e to the t squared dt, minus the integral from 0 to negative x squared e to the negative t squared dt. So now I'm looking at these two things separately. E, the integral from 0 to x squared of e t squared dt, minus the derivative of the integral from 0 to negative x squared e to the negative t squared dt. Okay, now these separately, let's define a function capital F to be the integral from 0 to x of e to the t squared dt. Then, rewriting this, this is d over dx. This is capital F of x squared. These two are the same thing. Why do I rewrite this? Because now the fundamental theorem, second fundamental theorem, says that capital F prime is e to the x squared. And then similarly, this one I can rewrite as well. D over dx of capital F of negative x squared. Okay, now we're ready to figure this out here. Okay, the chain rule says this should be f prime at x squared times the derivative of x squared, which is 2x. This one, the chain rule says f prime at negative x squared times the derivative of negative x squared, which is minus 2x. Okay, now f prime at x squared is e to the x squared squared, or e to the x to the fourth power. Then we multiply that by 2x. And then we subtract, but we got another minus sign, so let's turn it into a plus sign. E x to the fourth. Again, the negative x squared gets squared, so the negative sign goes away. So now we have a total of 4x e to the x to the fourth. Okay. I realize this was a lot of work for just this thing here, but you got to be very, very careful and only apply the fundamental theorem in situations when one of the variables, the bottom variable of integration is 0, and the top variable of integration is x, not some function of x. Okay, we'll do a few more like this because I know that this is kind of difficult to grasp. Let's find d over dt, the integral from 1 to sine of t, cosine x squared dx. Okay, so once again, we don't like functions in the variables of integration. We cannot work with them. So we gotta rewrite this. Let's define capital F of t to be the integral from 1 to t cosine of x squared dx. Why do we do that? Because the second fundamental theorem now says capital F prime is cosine of t squared. This statement here that I just wrote down is exactly what the second fundamental theorem says. When I do that, now I rewrite this as the derivative with respect to t of capital F of sine t, because that's exactly what this expression is. It's capital F of sine t. Now the chain rule says f prime of sine t times the derivative of sine t, which is cosine t. Now we know what f prime is. It's cosine of t squared. So this becomes cosine of sine t squared times cosine t on the outside. And that is our derivative. Okay. All right. These are kind of difficult. I understand that when these variables get changed around a little bit here, it's a little bit difficult. So I'm going to have a few of those on the worksheet as well, just to get you practice with that. And you'll notice that the previous final that I posted, there were some mysterious problems that seemed impossible to do, and the fundamental theorem is exactly what does those problems. So take a look at those again as well. All right.